So I'll be talking about several works, most of them joined with Eyal Lubetsky and one also with Nathaniel Berestitsky and Alan Sly. So we're going to look at the geometry of random graphs and certain deterministic expander graphs through the lens of how random walk behaves on them. And that turns out to be a very effective lens. So, classically, if you look at a graph, you ask, is it connected? But if the connectin is very thin, it's almost like the graph was disconnected. And random walk will detect that. So it turns out that behavior of random walk, relaxation time, mixing time, is a very good measurement for the robust geometry of a graph. And it's also just a natural process in itself. So some of our key participants will be the classical Erdős-Renyi random graph we'll come to, where every edge is present with the same probability independently. Somehow the simplest object to analyze in this context is a random three-regular graph. So random graph where or in general, you could have a d-regular graph where every vertex has the same degree d, and it's chosen uniformly among such graphs. And finally, something that I'll talk on are a celebrated class of expander graphs, the Ramanujan graphs. I'll recall the definitions and some basic properties, where we now understand random walk very well, even though things that seem more basic, like what's the diameter of this graph, we still don't know. So I'll come to these issues. Now if the graph is very, is symmetrical, like these Ramanujan graphs will be, it's transitive, then this point we start the random walk doesn't matter. But if the graph is the graph is like a random graph, then it matters a lot. And so, we'll see the effect of that when we analyze the random case. So we're going to look, as I said, at random walk on a graph and measure its convergence to equilibrium. So if our graph is regular, all the vertices have the same degree, then the equilibrium or stationary measure is just uniform, and so this mu is uniform. In general, for simple random walk, the stationary distribution is just proportional to the degrees. So every vertex take its degree, normalize, and we'll look at that mixing time. So the mixing time is the worst case mixing time, which we usually study. We'll be maximizing over the starting point the time until some norm, the total variation distance, which is written here, it goes below epsilon. So there are many ways to measure distance between measures. Total variation is the one that's somehow statistically most important. It tells you, if you look at all events, how the two measures differ. And there's an equivalent formula. It's just half the L1 distance between mu and nu. So yet another equivalent formula, if you try to do a coupling of random variable distribution mu and the variable distribution nu, put them on the same probability space, and try to maximize the probability that they're equal. Well, when you do that, the probability they're not equal is the total variation distance between the measures. So it has several interpretations, all of which are useful. Now, another measure that's often used doesn't have the same intuitive appeal, but a lot often easier to analyze, is just an L2 norm, and we'll come back to that ping pong between the L1, L2, and of course other LPs as well. So fixating on the total variation distance, an interesting phenomenon I'll talk about more in general Markov chains and in the random walks I'll consider is the cutoff phenomena, which is when the mixing time to first order doesn't depend on epsilon. So if I look at the distance decisionarity in total variation, we always know that once this goes below a half, it has to go down exponentially. But we're in fact interested in decay that's faster than that. So the cutoff phenomenon is when there's a small interval asymptotically negligible to the mixing time where all the action occurs. So the total variation distance goes down from near 1 to near 0 in a time which is negligible to the mixing time. And equivalently, this can be written this way. So T mix of epsilon is the time where this graph goes below epsilon. Well, we want that to first order that doesn't depend on epsilon. So the ratio of this time where we got to this very large epsilon or this time where we got to this small epsilon, the ratio of these should tend to 1 along our sequence of chains. So we really don't want to consider one Markov chain when talking about cutoff, but a sequence of Markov chains. So famous examples arise from card shuffling. You have n cards, and so random transpositions is one. Choose one card with the left hand, one card with the right hand, and transpose them. We'll see other chains. So we have but for every n you have that kind of chain. And again, all our chains will naturally come in families. And so cutoff refers really to a sequence or family of chains. So I said the first occurrence of these questions was in card shuffling. Actually, the first paper I'll quote is Diaconis Shashahani from early 80s. And then questions of how well a deck of cards is shuffled. The kind of shuffles they were considering were not just random transpositions, also riffle shuffles that are closer to real shuffles in a casino. And that was kind of one of the origins of the theory. So here are some of the earlier examples. So I mentioned random transposition. So you have n cards. Choose one with your left hand, one with the right, and transpose. It might be the same card. How many such do you need to mix? So there's an easy lower bound because a random permutation just has one fixed point in expectation. So until uniform random permutation. So you have to swap enough cards to get down to order 1 fixed points. So that's going to take half n log n because the coupon collector time is n log n each time you're swapping 2 cards. So that's the obvious lower bound, half n log n. Turns out, and it's not at all as obvious, that that's sharp. So Diaconis Shashahani showed that half n log n is actually enough to mix, and to first order it doesn't depend on epsilon. So if you want to get close to within 0.1 or 0.7 or 0.01, that affects the lower order terms in the mixing time, but the first order is just always half n log n. So in fact it's half n log n plus a constant that depends on epsilon that multiplies n. So that's the case there. And a nice coincidence is the next example was random walk on the hypercube, which also leads to half n log n. So random walk on the hypercube, let's do lazy random walk. So a point in the hypercube is just a sequence of bits, right? So we have n bits here. And we'll do lazy random walk on the hypercube to avoid periodicity problems. So what does that mean? We choose a coordinate uniformly at random, erase the bit there, and replace it by a uniform random bit. Or in other words, flip the bit with probability half and leave it the same with probability half. That's the same. Okay? So if you look at that chain, how long does it take to mix? Well, you see the connection to coupon collector, so it should be order n log n, but we want to be more precise. So the coupon collector takes n log n steps to collect all the coupons. That's the time, with a constant 1. That's the time where you will randomize all the coordinates. But it turns out that in this case, the mixing time has the same form, half n log n. Again, plus some constant that depends on epsilon times n. So why? Is there a question?
So do with the fact it's log n factorial?
In which case? Are you talking about the random transpositions?
Symmetry group has n factorial permutations. Log
So,
n factorial, that have to do with that?
so it has, in some weak sense, it has to do with that, but that's not a, that, so that counting provides you some lower bound, which is not sharp, but no, again, so the lower bound of half n log n, let me go about it more slowly. For the random transpositions, that was due to counting fixed points. So a uniform permutation has, right, has an expectation one fixed point, right? Every card, right? So when we start swapping, we start, say, with the identity. You can always assume that it starts with the identity. So everything is fixed point. Every time you transpose a pair of cards, you ruin two fixed points. So, or at most two. You might accidentally bring something back, but you ruin at most two fixed points. So, so now the classical coupon collector problem says that the number of cards, until touching all the cards, you need n log n rounds, but here we're doing 2. So if you will do less than half n log n, if you do 0.49 n log n, there'll be a large number of untouched cards. So far too many fixed points for the permutation to be close to uniform. Okay, so that was the easy lower bound. And the upper bound was actually using representation theory of the symmetric group. So that's how Dekonis Shashahani proved the upper bound, which allowed them to completely diagonalize the transition matrix. So that's that case. For the hypercube, it's also half n log n, but the half here is a little surprising because you think, well, to touch all the coordinates here I'm only flipping one coordinate at a time. So at half n log n, there's going to be about root n coordinates that have been untouched. But now we're not talking about permutations, we're talking about bits. So if you have a configuration of bits which are random except for root n that are, say, all zeros, but this location of these root n is completely random, that's already close to uniform. And if instead of root n I have n to the 0.49, that's already indistinguishable from random.
Are you always discussing the L1 or is this something?
Always L1. I'm discussing the L1, but in both of these cases, in fact, that's also the L2. In both these cases, the mixing time is L2. So when Daikonis and Shashahani, the reason their calculation worked out is that the lower bound in L1 matched the upper bound in L2, and then everything is sandwiched together. Okay. So this won't happen in the bounded degree cases, which is why these were only done now, and that was done 30 years ago. So the issue of the L1 versus L2, everything gets sandwiched together in these examples.
So the representation theory doesn't give you as much.
The representation theory gives you L2, right? Doesn't, and then if the bound you get, the upper bound for L2 matches the lower bound you have for L1, you're all done, which is what happened here. Okay. So for the hypercube, that's the answer. So you have cutoff on the hypercube. An example without cutoff is, say, simple random walk on a cycle. Right? So you have, and again, make it lazy to avoid periodicity. So from every node with probability half, you stay in place, and quarter you move to the right, quarter you move to the left. So this will mix in order n squared, but there's no magic constant in front of the n squared. So if you want to be epsilon close to stationary, you need to run about n squared times a log 1 over epsilon. So it will cost you a multiplicative factor to get closer. So that's an example without cutoff. So now we're going to switch to expanders, and we'll come back to other graphs. So expanders are graphs where the spectral gap of the transition matrix is bounded below. So again, it's not one graph, it's a sequence of graphs. We're looking at the transition matrix of simple random walk there. Right? So it's some matrix P, and we want the second eigenvalue of P to be bounded below by some 1 minus delta, and this should be true for all, so the delta should be uniform along the whole sequence. So that would be an expander sequence if the second, so we're talking about the transition matrix, so the top eigenvalue is 1, it's a stochastic matrix. The second one should be separated from that. And so in other words, the relaxation time, which is 1 over the spectral gap, should be bounded. Now on such a graph, there are pretty easy upper and lower bounds which are constant multiples of log n, but different constants. So the diameter, since the graph is regular, the diameter is at least constant log n, and you can't mix at a time which is less than half the diameter, so that gives you a lower bound. And an upper bound comes just from diagonalization and using L2 calculation. However, the issue was, well, is there an actual cutoff in these examples? So a particular case of interest is random regular graphs. So these are actually more easier to study than specific regular graphs like Cayley graphs. And their study was, there are earlier studies going back to Pinsker, but a lot was done by Bolobash in the 80s, who presented a useful way to sample these graphs. So if you want a 3 regular graph, you don't want to pick, write a list of all of them and pick one uniformly. You want an effective way to do this, which also helps in the analysis. And what you do is you just think of each node having 3 stubs, like half edges, and then you have a total of these 3n stubs, and n had better be even if we are going to get a graph like this. And then you take these 3n stubs and you just do a random matching of them, which is very easy to construct, right? You take these 3n and you can easily pick a random matching. You pick one and then you match it uniformly to some other stub and so on. And this process will create a random multigraph, so it might by accident match a node to itself or create multiple edges, but with constant probability that doesn't go to 0, it creates a simple graph, and conditional on that, that graph is a uniform deregular graph. So that's known as the configuration model, a very effective way to sample and also to analyze these random graphs. So that's right. That happens with, yeah, that's right. The graph is connected with high probability. So, and in fact, more than connected, it's very strongly connected in the sense that it's an expander with high probability. So that's been known since the 80s that this is, so that's right. So it's not just connected, but an expander. So I told you expander, what it means spectrally, but I should recall what it means combinatorially. An expander graph is a graph where for any subset which is less than half the graph, the number of edges to the outside is at least a constant fraction of the edges inside. So it's very well connected. So Berestitsky and Duret in OA, this was part of Berestitsky's thesis, looked at simple random walk on this graph and looked at the rate of escape from the starting point, and they found that the first order, the expected distance from the starting point, so this is a graph not of the actual distance, but the average, so the expected distance. So it grows at rate 1/3 until time 3 log n, where it reaches height distance log n, which is also the diameter of the graph, and then it just stays there. Of course, the actual distance is going to fluctuate. So this is the expected graph of the expected distance at every time. Now, the speed 1/3 is very easy to understand. Locally, this graph looks like a tree. So if you choose a vertex at random and look at a neighborhood of it, it will be a long time till you see any cycles. And on a three regular tree, a random walk indeed has speed 1/3, because from every, say this was the starting point, if you're here with probability 2/3 you move away, 1/3 you move closer, so the speed is 1/3. So that leads to this graph, and then direct conjecture that that time where you reach the maximal distance is also the mixing time. So, so the mixing time should be 3 log n, and everything I'm writing 3, but everything extends to other degrees higher than 3. The speed 1/3, in general, it will be replaced by d minus 2 over d, if you have d greater or equal 3. So this was proved by Lubetsky and Sly, that there indeed is cutoff on these graphs. And the interesting point is the cutoff happens exactly at the time when the maximal distance is reached. So it's easy to see it couldn't happen earlier because most nodes are at the maximal distance from the starting point, but it really happens at that time. And their analysis was based on using the non-backtracking walk, which will be a major player later in the talk. So non-backtracking walk is like simple random walk, but after you cross an edge, you're just restricted not to traverse the same edge immediately back. And so for the non-backtracking walk, the cutoff is exactly at log d minus 1n, which is also the same as the diameter to first order. So from this point, so this is kind of the background, and here we can diverge in 2 directions, the random case and the Ramanujan case. Let me actually start with the Ramanujan case. So this is joint work from last year with Lubetsky. It just appeared in GAFA. So I told you what's an expander. So now I'm going to actually do a different normalization. So instead of the eigenvalues of the transition matrix, we're going to look at the eigenvalues of the adjacency matrix, since we have a d-regular graph. That's just scaling by d, but that's the standard terminology in that field. So this is the second eigenvalue of the adjacency matrix, 0, 1 matrix. So there the maximal eigenvalue is d. So expander in this scaling means that the maximal eigenvalue should be separated from d. And that's equivalent to the combinatorial condition I mentioned before. Now, again, with lambda 2 interpreted as here.
One direction would be Cheever's inequality, but why the other?
So
That Cheever's inequality implies the gap, yes, but why does the gap
So,
Cheever?
so that's actually the easy direction, right? Because if you have a sparse cut, then that you can use that in the variational principle to show there's no gap. In fact, that is discussed very nicely in your paper with Percy, some Annals of Applied Probability, 1991. That's in fact the best place to read about it. Second best place is my second best place is my own book on Markov chains. No. Okay. No, but these, your paper and my book actually discuss there's a more general equivalence for reversible Markov chains. For the case of graphs, everything was explained very nicely in these early papers. Alon Milman actually did discuss the easy case, and then Alon's follow-up paper did the analog of Cheever's inequality. Okay, now the Alon-Bopana theorem, which first appears in detail in a paper under the name of Neely, but this is one of Noga Alon's pseudonyms. So this is and the name of his daughter, for those who don't know. So this is the statement that for any deregular graph, the second eigenvalue in this normalization can't get too small. So it's at least 2 root d minus 1 with an error that goes to 0. It's an error like constant over the diameter. So and that later led to a notion of Ramanujan graphs. So Lubovsky, Philip, Sarnak constructed graphs where lambda 2 was actually less than 2 root d minus 1, and their number theoretic construction led them to call these graphs, and more generally any graphs with these properties, Ramanujan graphs. So the terminology that they created in '88 was a connected d-regular graph where all eigenvalues except plus minus d are in absolute value less than 2 or at most 2 root d minus 1. That's what they called the Ramanujan graph. And again, the ones they were constructing were based on number theory. And Margulis had similar constructions independently at that time. So this was not done for all d, just in d minus 1 was prime. And later there were generalizations. In particular, Marcus Spielman's Srivastava a few years ago showed that there exist Ramanujan graphs for all d. Their proof is not constructive. It's a strange probabilistic argument which doesn't use the uniform measure. So it has some interesting measure, and it shows the probability is bigger than some exponentially small amount. So it proves existence, but it's not yet a construction, but we know they exist for all d. So this is one of the Lubovsky-Philip-Sarnak graphs. So this is a Cayley graph of PSL2 on field of 29 elements. And it's a 6 regular Ramanujan graph. It has about 12,000 vertices. And I can't show them all. So these are two views. So this is just a view of a piece of the graph. And this is a local neighborhood of one node. So see, locally it looks like a tree for a few generations. But of course, what we want to understand is what's going on here. Any questions? So this is an example. So these are, what you see in the front is the spectrum of the this Lubovsky-Philip-Sarnak graph. And what I want to emphasize is that the eigenvalues come with very high multiplicity. So that will come in later. There are other Ramanujan graphs with lower multiplicities. And one is shown here in the background, but the most interesting ones have high multiplicities. So this interval is normalized to be, it's basically the interval from minus to plus 2 root d minus 1. And there are trivial eigenvalues at minus d and plus d, which you can't see. Yes?
How many vertices PSL2 FQ have in terms of Q? Is it like Q to the fourth or something?
So it's, yeah.
Is it Q cubed or is it like Q cubed?
Yeah, so there are 4 variables, but there's a relation. So let's say the determinant is 1.
So it's like SL.
Okay. So this, I'm talking to you about work in the 80s, but there's some renewed interest in these expanders because of some unexpected applications to quantum computing. I won't go into these, but if you're interested, you can see some discussion of that in Sarnak's website. One fascinating thing that connects to those applications, and we still don't understand, is what is the diameter of these Ramanujan graphs. So there's a lower bound, right? If you have a d-regular graph, there's a lower bound of log base d minus 1 of n, because just by counting, you see how many vertices can I have at distance k? Well, it's at most d for the first step, and then d minus 1 to the power k minus 1 for the rest. So you'd need, so there's a straightforward lower bound of the diameter which is at least log base d minus 1 of the number of vertices. Again, and I'm going to look at the first order. One can be more precise, but I care about the leading constant now. So the diameter is at least that, and that's true for any d-regular graph, but what happens with Ramanujan graphs? So actually Sarnak had earlier conjectured in print that this lower bound is sharp, but we now know that's not the case due to work of his student Sardari, who found an infinite family of these graphs where the diameter is 4/3 log d minus 1. And so p here is d minus 1 in these examples. However, we still don't know what is the highest diameter achievable. The best upper bound is twice the lower bound, and that's still the case now, 30 years after the initial work. So I'll come back to this issue.
And so you mentioned that eigenvalues have high multiplicities and some other eigenvalues. And so why are eigenvalues below some leading eigenvalue important?
Okay, they will come in our analysis of random walk. So.
But if it's like asymptotic property, are they important?
So if you had it turns out we can get around it, but I'll come back to this point. Okay, so I remind you that we're looking at cutoff, so we want to see if the understand the mixing times, and cutoff corresponds to the mixing time, not depending on the epsilon, to first order. And for simple random walk on d-regular graphs, so one important result is by Joel Friedman in 2008, who proved a conjecture of Noga Alon that said that random d-regular graphs are weakly Ramanujan. So we don't yet know if a positive fraction of them are Ramanujan, but we know they're weakly Ramanujan, so up to this little o of 1 error, most of them are there. So that's one thing. One conjecture I made in 2004, which we still don't know, is that cutoff holds for all transitive expander graphs. Now, when I made that conjecture, of course, there were no counterexamples, or I wouldn't make it, but there were also no examples. But I still made it anyway with no examples. So now we at least have some examples, namely there is cutoff for all Ramanujan graphs. As I'll mention, no, but there are large family of transitive. So the LPS Ramanujan graphs are transitive, but certainly there are lots of Ramanujan graphs that are not transitive. So I'm saying the intersection. So if they're Ramanujan and so the cutoff holds in all Ramanujan graphs. In particular, it gives us families of transitive expanders.
Transitive means group of seemingly transitive?
Exactly. Right. So transitively means that exactly what you said, or for any two nodes, there is a graph automorphism that maps one to the other. Sorry, I should have said that. Thanks. Okay. So Shayan Noves-Garan conjectured that Ramanujan graphs will all have cutoff, and that was led to this work. So, as we discussed earlier, in the early examples of cutoff, it was done by sandwiching L1 and L2. That really doesn't work in these examples. So this is a graph of the actual L1 and L2 distances on that LPS graph I showed you before, and you see that they decay really at different times. And we understand now exactly the asymptotics, and so the decay happens at different times. It's all a constant log n, but they're just different constants. So you can't get cutoff by L2 analysis, which distinguishes this from all these high degree cases done earlier. So the L2 distance goes down. There is cutoff for you can't get cutoff in L1 just by doing L2 analysis. So it turns out there's cutoff in L1, there's cutoff in L2, they happen at different times. The key is that if you go to non-backtracking walk, then for non-backtracking walk, it turns out the L1 and the L2 do have cutoff at the same time. And then you can use that to go back and analyze the simple random walk. So that's the key to the proof. And so what goes wrong in simple random walk in low degree graph is there's too high probability of just going back and forth when the degree is small. And that blows up the L2 norm. So if you just rule it out by going to a non-backtracking walk, you fix that, and then L1 and L2 can match. And then you analyze the non-backtracking walk, and then you have to go back to use that to analyze the simple random walk. So that's the basic technique, and it allows us to prove that there is cutoff in any deregular Ramanujan graph. So that's the result. So you have this d over d minus 2 log d minus 1n. So again, there is cutoff at the earliest time it could possibly be, because that's the time it takes to reach the outskirts of the graph, the diameter of the graph. Because we are moving at speed d minus 2 over d, and the graph has diameter log d minus 1n at least. So, so I said the outskirts, and I have to be careful here because we don't know the diameter is log d minus 1n. In fact, there are examples where it's higher. So what's going on? Let me jump to this corollary, which explains what's going on. So although we don't know what is the diameter, we know in some sense the effective diameter. So here is one corollary of a result, and it's this corollary, I should say, was proved independently by different methods by Sardari. So what does this say? Fix a node x in a Ramanujan graph, with a large n, and then to reach most vertices, you need to go at least distance log d minus 1n. But it turns out that that's enough to reach most vertices, although we don't know if it's enough to reach all vertices, but 1 minus little o of 1 are reached at that distance. So if you look at those where the distance over log d minus 1 is not close to 1, those are a negligible fraction. Now, one thing to be careful here, there's a real distinction between what I'm calling this effective diameter and the diameter. And go back to a simple graph we understand. It's the hypercube, right? In the hypercube, the distance between the all 0 and the all 1 node is n. But if you, from any node a distance a little more than n over 2, you reach almost all the hypercube. So reaching most vertices and reaching all vertices could be different. How different could it be? At most a factor of 2, right? Because if from every node I reach most vertices in some distance, and it's true for the other one, then most vertices have to lie somewhere. So it's easy to get from this to recover actually a known bound. So this bound was actually proved in the 90s by Chang, Faber, Mantufuel for all Ramanujan graphs. It was already known by LPS for their graphs. But this is a general upper bound of twice log d minus 1n, and it is recovered from this theorem. This theorem has additional information. Questions?
So do you know anything about the little o of n?
So yes, but maybe that's an advanced question. So. So, if you put the real, positive epsilon here, then this will be a tiny fraction. So it will be less than n to some power less than 1, which can be controlled in terms of epsilon. Okay, so I'm going to skip this, but I want to say that these theorems also hold for weakly Ramanujan graphs, And also one can allow a few large eigenvalues as long as they're not too close to 1, and the rest of the graph is weakly Ramanujan. So in particular, if you want, you can recover the Lubetzky-Sly results on the random graphs from this theorem because it applies to, I'm talking about from this theorem, the mixing time theorem, because it applies to weakly Ramanujan as well. We can now analyze the LP distance to stationarity for all p. So, and for every p you have cutoff at a different time that really varies with p. So maybe I'll skip that and go to I mentioned that the key tool is non-backtracking walk. I won't have time for much detail here, but so analyzing non-backtracking walk is related to this non-backtracking matrix. So that's a larger matrix. So if capital N here is the number of directed edges in the graph, so that's d times little n. And the non-backtracking matrix, before normalization to an edge u v x y, it's just 1 if v should be equal x, but u should be different from y. And then these matrices have been used in number theory, and one classical result of Hyman-Bass is a relation between the interesting eigenvalues of B. So B has a lot of eigenvalues, but some of them are uninteresting. I'll come back to them, either trivially large or trivially small. And all the interesting ones satisfy this kind of quadratic equation. So if lambda is an eigenvalue of A, of the original adjacency matrix, then and theta is an eigenvalue of V, then it solves this equation. In particular, you see that the interesting eigenvalues of B will come in conjugate pairs, conjugate solutions of this quadratic. So there will be, and another thing, all the interesting one will have magnitude square root of d minus 1. So maybe I have some picture. So the eigenvalues, this is the LPS case, so the eigenvalues come in pairs, and these lines are just for illustration. The eigenvalues are actually all on this circle of radius root d minus 1. And this is a case of high multiplicity. This is a different Ramanujan graph where you have low multiplicity, and so you don't see this kind of separation. Anyway, so I'm going.
This identity of Bass for this particular kind of graphs, or
So this is identity is for any d-regular graph. Okay, and we have a statement which is in the next slide, which adds some more detail to the Bass identity. I should say there are a lot of related works, and I'm not surveying all of them here. But this is our refinement of Bass's theorem. There are, as I said, other refinements you can find in the literature. And there's a Bass theorem, a variant of that is known as Hashimoto theorem. And there are many communities who found this non-backtracking useful. Anyway, this is our refinement of this Bass theorem, which says that the Jordan form of the matrix has, so there's one trivial eigenvalue of d minus 1, because this is a d minus 1 degree graph. And then there are various unimportant plus minus 1s that are eigenvalues. But then all the interesting ones come in pairs. So these are these thetas that are solutions of this kind of equation. So there are n of these pairs. But the important thing is the Jordan form has only 2 by 2 blocks. So that comes back to Pavel's question, why do I care about the multiplicity of the smaller eigenvalues? It turns out that if the eigenvalues had large Jordan blocks, we would be in trouble with calculating high powers of the matrix. So we need to know that the Jordan blocks are small. Now, if the eigenvalues came with low multiplicity, it would be automatic that the Jordan blocks are small. But because the eigenvalues come with high multiplicity, it's not automatic. It's something that you need to verify. Now, this is always true. This doesn't assume it's Ramanujan. However, so this is for any deregular graph, connected deregular graph. The interesting thing in the Ramanujan case is we can say exactly what are these off-diagonal terms. They're all equal to d minus 2. So we were kind of amazed that this explicit thing was not observed before. But once we observed it and showed it to people, especially Alex Lubotsky, they found much deeper explanations behind it related to Hecke algebras. And I invite you to look at the follow-up paper by Lubotsky, Lubetsky, and Parchenevsky that extends this to Ramanujan complexes from this idea. Okay, so once you have that, one can easily use that to explicitly calculate the distribution. I'm going to skip this spectral calculation and get the cutoff results. I'm going to end this part of the talk, and then I have 10 minutes on the random case, with advertising. Here's one curious fact, which is from my book with Russ, which we used. So take the non-backtracking matrix of a deregular graph. In order to understand its spectrum, it would be nice if it was symmetric, but it's not. However, it has a close relative which is symmetric. So if you take the matrix, it's invertible, multiply the inverse by d minus 1 and add b. This matrix C turns out to be symmetric. So then you can use the diagonalization of C in order to compute the eigenvalues of B and understand the structure of their spectra. Okay, so it's all about that, and I want only have a time to give a bit of a hint on the random case.
So this fact about matrix being symmetric, this implies that Jordan blocks L size 2 will less, right?
Yes. Okay, so I'm going to switch gears and tell you at least the results in the random case. So this is the Erdős-Renyi random graph, which has a phase transition. So again, every edge is present with probability p and removed with probability 1 minus p. And the important point is when p is around 1 over n, then the largest cluster is size n to the 2/3. Before that, it's logarithmic. And after that, the largest cluster is linear in n. And we'll be interested in this supercritical phase when p is a constant over n and that constant is bigger than 1. Any question? So, okay. So what about random walk on this graph? So the critical case is very interesting, and I've worked on that in the past, but I want to focus on the supercritical case where so the size of the giant component is linear in n. The mixing time is quadratic in log n. That was proved in 2 independent papers, first by Fontoullakis and Reed, and shortly thereafter by Beniamini, Kozma, Wormald. And in fact, the reason for this is bottlenecks. So the random graph has nodes that are related by long paths of length log n to the main body of the graph. So if you start at the end here, you're basically doing one-dimensional random walk, so it will take you time log squared n to reach this main body. So that easily gives you a lower bound of log squared n. The content of those papers is showing that this lower bound is sharp. So that once you come here, the mixing time is log squared n. Now, even if you remove these, remove all the leaves, go to what's called the core of the 2 core, still you have even inside this, what I call the body of the graph, or it's known as the 2 core, you have also long paths here of length log n. So if you start in the middle of such a path, again, you will, it will take you time log squared n to reach most of the graph. However, Fontoullakis and Reed asked whether this log squared n is really due to bad starting points. So these are bad and these are bad, but maybe most starting points will mix faster. So that's what they conjectured, and Funtulakis and Reed, and that's what we proved. So if you start from a typical vertex, then you mix in time which is order log n instead of log squared n. So that was one result. But then what we really worked hard to show is that when you start at a random point, not only it's log n, but then you have cutoff for these random starting points. So there's a specific constant times log n. And this is itself a story I don't have time for. It relies on this structure theorem for the giant component. So I just have time for maybe tell you one more story, and then I'll finish. So it turns out in this case, the mixing time doesn't happen when you reach the maximal distance. And what's behind this is an interesting irregularity in random walk on random trees. So the local structure in these graphs is still that of a tree, but it's not a regular tree, it's now a Galton-Watson tree, a branching process. And what happens in this Galton-Watson process is that if you run a random walk on such a random tree, it will explore only a small part of the tree. So this tree grows exponentially, but there'll be a subtree of smaller exponential growth where the walk is concentrated. And that's work with Lyons and Pimentel in the 90s, which, let's see, I want to mention that work. So that's here. So this, again, according to this David Aldous dictum, that the best warm-up for understanding large finite graphs is first to understand infinite graphs. So in the 90s, I worked with the Lyons and Pimentel understanding random walks on Galton-Watson trees. And this was the foundation of understanding random walks on the random graphs now. So since I'm out of time, I just want to show you just one example of what's going on in the simplest case. So that will be an example for non-backtracking random walk on a Galton-Watson tree. And this is going to be, well, I have to finish. So you have a tree where every node has either 2 children or 3 children equally likely. Okay? So this with probability half and this with probability half. So say you start with 2 children, then this has 3, this has 2, this has 2, this has 3, and so on. Okay? Now let's go on to this, to some very deep level k. So at this level, how many nodes we will have? Well, on average, every vertex has 2.5 children. So the number of nodes we will have will be of order 2.5 to the k at level k. However, the random walk will see a very small, tiny proportion of these. So I'm just going to simplify and look at non-backtracking walk. Simple random walk is harder in this case. But so if you look at non-backtracking walk on this tree, as it moves forward, each time it will encounter a vertex of degree with 2 children or with 3 children equally likely. So the non-backtracking walk will concentrate on nodes here where in their history, half the nodes have degree 2 and half the nodes have 2 children and half the nodes have 3 children. So how many vertices are there like that? So if you look at the vertex like that, the chance of falling into that is going to be 1/2 to the n over 2 times 1/3 to the n over 2. So this is a typical vertex that has half its nodes. A typical path here has half its nodes 2 children and half 3. So if I ask what's the chance of falling into such a typical node when I do the non-backtracking walk, it's this, which is 1/√6, I'm sorry, to the k. 1/√6 to the k. So what you find from this consideration is that non-backtracking walk is supported on a tree whose growth is smaller. It's √6 to the k instead of 2.5 to the k, right? So check √6 is really smaller than 2.5. So there's this smaller subtree that the walk concentrates on. And this is true also for simple random walk. And this phenomenon reappears when we look at mixing in finite graphs because the local structures of these Gauss-Watson trees, and it actually delays the mixing time beyond when you would expect it to happen according to when you reach the right distance. So, you know, the details here are one of my favorite stories, but I've run out of time. So thanks a lot for your attention.
Thanks a lot. Questions for our speaker?
Yes.
What are the current references for this work on mixing times on random graphs?
These papers are all in the archive. So this is a paper I mentioned in the beginning with. So the random case was with Lubetsky and Berstitsky and Sly. Okay, and it's called Random Walk on the Random Graph. You can find it in the archive. It's appearing in Annals of Probability. By the way, if Scott's here, so the paper I promised from the first day has been uploaded today, so it should. So a day late, but.
8:30 tonight.
If the archive still functions as it's supposed to, yes.
That's a good question. The delay.
So it was uploaded this morning. That's what I can guarantee. So sometimes they upload the same, sometimes it's available the same evening surreptitiously. If someone can't wait, just email me and I'll send you it by email. Or even faster, email Nina and she will send it to you. Yes?
The reduction from log squared n to log n in the typical, is it because the typical distance between the high degree nodes is now constant as opposed to log n?
Right. I mean, but you have to say that also the random walk, so there are these long paths, but it doesn't find them. It doesn't venture into them. It doesn't go. So
But it doesn't prevent it from mixing because they're too small.
they're too small, exactly. But this was actually quite hard to prove.
So you're saying there's no cutoff phenomenon when I start from the worst case?
Right, because on a path there's no cutoff phenomenon. So if I have a path of length k, it takes me time k squared to cross, but I can't say, oh, by time 10k squared I'll definitely be there. Might be longer. So because the dominant factor is they're just crossing a long path, so there's no cutoff.
There's a delayed cutoff. If you wait enough to go beyond this initial bottleneck,
Then, okay, but the cutoff happens at a scale which is smaller than the time it takes you to cross this initial bottleneck. So no one would call that a real cutoff. Any other questions?
Okay, let's thank Yuval for a great show. We have talks next week and a colloquium tomorrow.
Well,